Welcome back to this video on the applications of Laplace transform. In the last video we have seen how to solve a heat equation, which is a parabolic equation in the domain, spatial domain between 0 to 2, x between 0 to 2 and t positive, and that is actually you consider physically that is a rod of 2 meters. With the boundary conditions we keep 0 temperature at both the ends, that is u0 t 0 and u2 t 0, okay. And then at time t equal to 0 initially you keep the rod temperature as given, that is 3 times sin 2 pi x as that is given, so as the initial condition. So this problem we have solved by applying Laplace transform. It so happened that when you apply the Laplace transform you see that u bar of xs, Laplace transform of this temperature function u bar of xt, that is that becomes Laplace transform is u bar of xs, which is 2 arbitrary constants involved in it as in the complementary function when you solve the ordinary differential equation, and c1 times e power root s x and plus c2 times e power minus root s x plus some particular solution, okay. And after now you apply the boundary conditions and get your c1 and c2. If c1 and c2 both are non-zero, then you should be able to invert this function u bar of xs. In the last video, in the last example, c1 c2 becomes 0, so you have only that particular solution that you invert it and you get your solution. If c1 becomes 0, for example you look at, let us look at the equation, let us look at the solution, u bar of xs is this. If c1 is non-zero, and you have to evaluate this Laplace inversion of e power root s sx, okay, x is positive, so for which Laplace transform does not exist, okay, because if you look at that Laplace inversion integral for this one you do not, so you will not be able to this is actually you contour integration technique may fail, this Bromwich contour may fail to evaluate this, otherwise the integral as such may exist, okay, Laplace inversion. So you cannot simplify directly that Laplace inversion, you cannot you may not be able to simplify with the usual techniques of contour integration. So but if c2 is non-zero and you have this exponential of minus e square root s times x, x is positive, for which Laplace transform inverse Laplace transform exists, that is what we will show you how to evaluate this Laplace inversion for this, okay. For other boundary conditions where c1 and both c1 c2 are non-zero, in that case or c1 is 0 case, you may not be able to write explicitly as a function of t, but as a solution will be in terms of an integral as a inverse integral, okay, inverse transform of this for which you may not be able to get it as an explicitly by the contour integration, you just have to leave there. But if for some boundary condition if c1 is 0 and c2 is non-zero, you can evaluate explicitly because of this thanks to this contour integration technique. So let us look at this Laplace inversion of this function, Laplace inversion of e power minus a root s where a is positive. So this is what we will see today. So this is Laplace inversion of e power minus a root s, which is a function of t. So by definition this is 1 by 2 pi I times integral c minus I infinity to c plus I infinity e power minus a root s e power s t ds. So this is the integral you have to evaluate. If this is positive minus a, if it is positive, then you have to leave this integral as such, formally you have this is the solution as a function of t. If this is minus a times root s for the exponential, you can evaluate this as in an explicit form by the contour integration. So let us look at the Bromwich contour, so which is SC, where C is because of this function having 0 is the branch point, otherwise in this half plane this is analytic function. So you can consider C anything positive, okay, C is anything positive here, and you look at this quantity, this is a contour, you look at it, okay. So if you look at this contour, this is your R and this is your R, okay. So you look at this piece and this piece and this piece. Okay. 0 is the branch point, because of this root s is having multi-valued functions, multi-valued function. So, you have to cut this 0 from this plane, complex plane, so that you have only single valued function. So, what you do is you try to remove this, you make a branch cut from the, this is the cut you have to make between 0 is the branch point and also infinity is also branch point. So, in the complex plane infinity you can think of anything anything which is not finite. There is no differentiation between minus infinity plus infinity here. So, let us connect 0 infinity this way. If you remove from the complex plane, you have this plane with this minus, this is a slit, this is removed. So, you consider this contour is a circular arc, and then you come like this and make a small circle around this, like this you make a small circle, and then you come back here and then make again a circle of radius r, and then attach it here. So, this is the contour you have. So, it is if you do it from here, c minus I infinity plus c plus I infinity over this, and then this you call this gamma 1, and you call this gamma 2 and gamma 3, this piece between this to this, and this is between gamma 4 and this is gamma 5, the circular arc circle, and then this is gamma 6 and gamma 7 and gamma 8. So, you have a gamma that is composed of union of all these gamma i's, I is from 1 to 8. So, that is your closed contour. So, what I do is I consider to evaluate this integral. So, that is over this gamma 1. Okay. So, what I consider is the integral e power minus a root s e power s t ds over gamma. So, if I consider this, so this is actually equal to now if I consider this integral over this gamma, because there is no pole for this function, this is analytic inside this closed inside the domain of gamma. Okay. Gamma inside gamma, the function e power minus a root s and e power s t both is analytic, because of this analyticity by contour Cauchy residue theorem, you do not have 2 pi times residue of there is nothing. So, it has to be equal to 0. Okay. So, this implies, so let us make this 1 by 2 pi here, we can add it at the end. So, this is 0. So, that means over gamma 1, that is actually your as r goes to infinity, if you consider this as your r radius, as r goes to infinity, gamma 1 becomes c minus infinity to c plus I infinity. Okay. So, gamma 1 plus gamma 2. So, what happens to gamma 2? Let me as r goes to infinity, gamma 2 becomes gamma 2 goes to 0 as r goes to infinity. So, that is what you will see. Initially you see that this piece as r becomes bigger and bigger, this is vanishing. So, you will see that this r2 is going to 0. Similarly, r8 is going to 0 as r goes to infinity. So, it does not really matter. Okay. So, you need not consider this gamma 2, gamma 8. So, you have to worry about gamma 3, gamma 7 and gamma 5, gamma 4, gamma 6. Okay. So, gamma 3 over gamma 3 plus gamma 4 plus gamma 6. Okay. Let me plus I add it here, and then let us gamma 5 and then plus gamma 6 plus gamma 7 of this function e power minus a root s times e power s t ds, which is equal to 0. So, let me calculate it over gamma 3. What happens to over gamma 3? Let us look at in this gap, I will write everything what happens to gamma 3. Integral over gamma 3. What is gamma 3? Gamma 3 is a curve. Let me write it here. So, if you look at the gamma 3, so gamma 3 if you look at, so this is e power, okay, first of all, once you make a cut, S is the complex plane, once you make a cut in polar coordinates, this is r into e power I theta, theta is between minus this is pi to or minus pi to pi. So, this is how you have once you cut this pi thing you cut, right. This is 0, this is theta equal to 0, and you come back here, that is pi, and you come back here, this is minus pi. So, you have this is your theta between minus pi to pi. This is this function is root s is a single valued function, okay. That is this divided by this root s, which is equal to this where theta is this and r is positive. So, this is the domain of the complex plane. So, full S plane I write it as this is how you represent in the polar coordinates. Now, what happens if you look at this gamma 3, this is a circular arc. Gamma 3, if you parameterize gamma 3, what happens to if you parameterize, that is r times, that is fixed r. So, r times capital R is that distance, e power I theta. What is theta? Theta is between that is between straight, that is pi by 2 to pi. So, if you look at this theta is pi by 2 here, and when you come here, this is theta 2 is this is pi by 4, okay, up to here, this is up to here pi by this is pi, this is 0, pi by 2, and then this is pi. So, we have this. Now, if you look at this e power, so what is your domain? So, what is your integrand is e power minus a times root s, s is this, okay. Root s is root of r times e power I theta by 2, okay. And then and what happens to e power st? S is e power r times e power I theta, and then ds is s is this. Once you parameterize, ds is over that curve gamma 3. So, s is actually this is a parameterization for this, s equal to this, okay, s equal to this, you have ds will be r times I e power I theta d theta. So, you can write this, so integral over minus pi by 2 to pi by pi, and you have this this one times, and now ds I write r times I times e power I theta d theta. So, this quantity, if you look at because theta is theta by 2, theta by 2 is between pi by 4 to pi by 2, okay. So, within this quantity is e power I theta by 2 is real part is always positive, cos theta by 2 is positive, okay, because this is positive and you already have e power minus times a is positive, root r is positive, this quantity real part is positive. So, what is left is e power I times something, okay, e power I sin theta, that part when you consider this modulus that goes inside, that is less than or equal to that inside, that will be 0, that will be 1, e power I times sin theta by 2 part, that is actually becomes rather e power, what you have is e power minus a root r I sin theta by 2. So, this part is actually 1 when you consider the modulus, okay. So, with that this is the only contribution cos theta by 2. So, e power minus a root r e power and you have cos theta by 2, that is positive quantity, and you have positive quantity. And then now what happens to this e power r theta, e power r cos theta, when theta is between pi by 2 to pi, this quantity cos theta is negative between this theta, okay. So, when theta is this, cos theta is negative, so this quantity is negative times minus, so e power negative quantity power r, and of course you have another quantity, this is e power r times I sin theta. So, that when you take the modulus, that is going to be 1, okay. So, when you consider this modulus which is less than or equal to this modulus inside, okay, and of course you have to put it here. So, that this quantity goes I time mod I is 1, e power I theta mod is 1, and you have this quantity, that is actually the product of these two, product of these two, this one into this. Okay. So, this quantity, because this is the exponential negative and this is also exponential negative, that goes to together, this goes to 0 as r goes to infinity. This is exponential growth, and you this r does not matter. So, you have r divided by exponential positive r whatever. Okay. So, as r goes to infinity, that goes to 0. So, the contribution over gamma 3 as r goes to infinity is also goes to 0. So, that means the contribution over this means this implies integral over gamma 3, that e power minus a root s e power s t ds, which is that goes to 0 as r goes to infinity. So, you have seen as r goes to infinity, gamma 2 anyway goes to 0, this piece, this straight line piece, and this circular arc as r over gamma 3, that is also goes to 0 as r goes to infinity. By the same technique, over this this circular piece, which is actually between minus pi by 2. So, in this case what you have to consider is same parameterization, gamma, what is that, gamma 7. Okay. That is gamma 7. If you consider gamma 7 here, so parameterization is minus pi by 2 to minus pi. So, even in this case you see that minus pi by 2 to pi, minus pi, or minus pi to minus pi by 2. So, smaller you have to consider. So, in this case minus pi to minus pi by 2, if you consider, you see that cos theta by 2, this is also positive, this is also negative. Okay. So, again this goes to 0 as r goes to infinity, the same technique. So, you see that gamma 3 plus gamma 7 both are going to 0 as r goes to infinity. So, this quantity is not contributing, and this quantity is not contributing, this quantity is not contributing, integral over this part is not contributing. So, you have to look at gamma 4 and gamma 6 and gamma 5. Let us look at gamma 5 now. Gamma 5 is also is going to 0. So, integral over gamma 5 e power minus a root s times e power s t ds. So, for which if you consider now gamma 5, if you consider gamma 5 as your arc, circular, it is a arc, if you look at that as a circle, what is its parameterization, s equal to let us look at this small r. You consider a small circle here, that is small r, let us say some small r, this is equal. So, parameterization is r times e power I theta, theta is between 0 to 2 pi. Okay. So, let us look at what happens here. Integral over gamma 5 becomes integral over 0 to 2 pi times e power minus a times root s is root r times e power I theta by 2 times e power r into e power I theta times t. Of course, here also we have t. Okay. T is anyway positive, so it does not matter. So, this e power I t ds is I times r e power I theta d theta. So, in this case whatever may be as r goes to 0, as r goes to 0, this is the bounded quantity, this goes to 1 and this goes to 0. So, this quantity is anyway as r goes to 0, as r goes to 0, that means you diminish this, as r goes to infinity, this small r goes to 0 and this gamma 4 becomes lying on the line here on the negative x axis, and gamma 6 also coming from the bottom. The limit this piece becomes the 0 to infinity, which is going to match with negative x axis from the bottom. And gamma 4 is a positive, it is a piece from 0 to infinity, that is lying from, it is coming from a top, from this part it is lying, it is going to map with negative x axis. Okay. It becomes a negative x axis from the top, and the gamma 6 is the negative x axis from the bottom. So, as the limiting value of that, as r goes to infinity, small r goes to infinity. So, as small r goes to 0, this quantity is going to, so integral over gamma 5, the contribution of this integration over this circle, small circle is also 0. So, only thing is what is left is gamma 1, gamma 4 and gamma 6 together is 0. So, what we have is this 7 is gone 0, 3 is 0 and you have gamma 5 is 0. So, you have what you have left is gamma 1, gamma 5, gamma 6, that together is 0. So, this implies integral over gamma 1 plus integral over gamma 4 plus integral over gamma 6 times e power minus a root s e power s t d s is equal to 0. So, this is what you have right now. Okay. So, what is gamma 1 as r goes to, so let us look at what happens to this gamma 4. Gamma 4, so for this you look at gamma 4, what is its parameterization. So, you look at the gamma 4, it is S is there, the piece, that piece over the negative x axis is that is actually, that is becomes a real number times e power I pi. So, this is the parameterization for the negative x axis from the top, because it is a pi, e power I theta, theta is pi. If you take it minus I pi, this is coming from the negative piece. This is your x axis, and this becomes that if you come from the bottom side, that is the parameterization for gamma 6. Gamma 6 you have to consider with minus pi. So, this is let us look at only gamma 4 is this. So, what is ds? ds is simply x is constant, x is actually varying. So, you have a dx times e power minus I pi is minus, it is right now it is I pi for gamma 4, and dx times cos pi, that is minus dx, sin pi is 0. So, this is what you have. So, what happens to their integrand? Integrand is 0 to infinity. So, x is between 0 to infinity, right. So, if you look at gamma 4, gamma 4 is actually coming from this side. So, you look at this direction, gamma 3 is gone, gamma 4 is actually this way coming from this side, and you like this it goes. So, gamma 4 is coming from 0 to infinity. So, 0 to infinity means it is minus of gamma 4. So, you have to look at gamma 4 as the minus of gamma 4 is this one, okay, between 0 to infinity. If your actual gamma 4 is infinity to 0, okay. So, you have to write infinity to 0. Let me write it as infinity to 0, okay. So, x is between infinity to 0. So, it is actually 0 to infinity, because of the direction I am writing integral from 0 to infinity, infinity to 0, okay. Actually it is between, you do not write limits, this is actually r, small r, this is actually capital R. So, let us write from r to r. So, let us use this, strictly speaking this is between small r to capital R. So, you have integral is actually gamma r, that is from small r, big R to small r, that is over gamma. So, integral over gamma 4, this function e power minus a root s times e power s t ds is actually equal to this, integral r to r, and e power minus a times root s is root x times e power I pi by 2. So, e power I pi by 2 is cos pi by 2 is 0 plus I sin pi by 2. So, this you have I, and you have e power s is x times minus x. So, you have a minus x here, cos pi is minus 1 plus I sin pi is 0. So, you have e power minus x. Of course, you have s t, t is there, you have ds is minus dx. So, you have put minus, you have dx. So, this is the integral that it has become. So, as r goes to infinity, e power minus a root s e power s t d s goes to integral, this is from, as this goes to 0 to infinity of e power minus x t times e power minus a root x I dx, as r goes to 0 and small r goes to, big R goes to infinity because of this, okay. If you look at this gamma 6, if you look at the gamma 6 same way, you have x is x times e power minus I pi is the your this thing, and this is your parameterization for this. Integral over gamma 6, now e power minus a root s e power s t ds, this is equal to, and you have this is now because of the direction coming from this to this. So, you have r to r. So, integral from small r to big R times dx is minus dx. Okay. So, what is ds? ds is cos pi, that is still minus dx, and you have what happens to e power minus a times root x, and you have root s, and e power minus I pi by 2, that is cos pi by 2 is 0 minus I. So, you have a minus I, that is going to be plus I, and here exponential s is e power x cos e power minus I pi is minus x t. So, this is what is the integral. So, this implies you have integral over gamma 6 e power minus a root s e power s t ds. This goes to and minus 0 to infinity e power minus x t e power plus a root x times I dx as r goes to 0 and capital R goes to infinity. So, what happens to the last one, which is gamma 1 e power minus a root s e power s t ds, this goes to c minus I infinity to c plus I infinity times e power minus a root s e power s t ds as r goes to infinity, small r goes to 0. So, what you have right now, so because this all these 3 together is 0, this is what you want. So, you can simply multiply this 1 by 2 pi I times over gamma 1, that is c minus I infinity to c plus I infinity e power minus a root s e power s t ds, this is equal to minus times. So, you bring this minus, one is, so if you take this minus, this becomes the plus side, this take it to the other side. So, that is going to be 1 by 2 pi I times integral over gamma 6, that is 0 to infinity e power minus x t times e power I a root x dx, and see this becomes, this goes to the other side, that is this, and you have the other one is minus, that is plus, because this is going to be plus, and when it brings to the other side, that is minus 1 by 2 pi I common, because I multiplied all the 3 quantities. So, you have here also 0 to infinity e power minus x t e power minus I a root x dx. So, what is this value? This value is actually this integral value, what you are looking for as the Laplace inversion of the function of e power minus a root s as a function of t is this quantity. So, this is equal to 1 by pi integral 0 to infinity u e power minus x t, and this minus this will give me 2 I goes 2 I times sin a root x dx. So, this is the integral you still need to evaluate. If you evaluate this one, I know what is the Laplace inversion of this. Okay. So, to evaluate this, let me use the Fourier transform. This is actually Fourier, this is actually what Fourier sine transform. If I just use the some this is actually your Laplace inversion of e power minus a root s as a function of t. I need to find this, I need to evaluate this integral. To do this, let x equal to, you call some u square, some new variable. If I use the new variable, what happens to your dx? Dx will be 2u du. So, this I, let us call this I. So, you have I equal to 1 by pi times integral, because of this 0 to infinity only, and e power minus x is u square. So, you have u square t times sin a times root x is u a u dx is 2u du. So, you have u here comes here 2 u and you have du. So, this is exactly equal to root 2 by pi times 1 root 2 by pi with this is actually Fourier transform. So, how do I write Fourier sine transform f s of u times e power, or if I use as a function of x u, you can write it as a function of. So, let me write this as same way u times e power minus u square t as a function of a, okay, function of a, because this at the end you get a function of a. T is a constant, given constant, a is the variable. So, a is because of a is a variable. So, you have this is the Fourier sine transform of this function. So, if you write this as a Fourier transform in new variables, if f of s as a function is x times e power minus x square times some t is a constant which is a function of xi. So, this is what you have, okay, Fourier sine transform of that. And if you actually consider Fourier transform of x into e power minus x square t as a function of xi, if you actually write what is the definition, 1 by root 2 pi integral minus infinity to infinity x into e power minus x square t e power minus I xi x dx. Okay. So, this is your definition of Fourier transform. This is Fourier sine transform, and let me look at the Fourier transform and I relate this, I calculate this one. So, this is equal to if you actually split this as 2 pi times 0 to infinity x into e power minus x square t e power minus I xi x dx plus 1 by root 2 pi. So, let me use this as a factor and then plus minus infinity to 0 x times e power minus x square t e power minus I xi x dx. So, here if you try to replace x by minus x, so you have x by minus x, this and dx will become plus and this becomes plus and this is as it is, and because of x by minus x this is going to be infinity to 0 and that makes it 0 to infinity with a negative sign. Okay. So, this is equal to 1 by root 2 pi and this becomes integral 0 to infinity x e power minus x square t, and this quantity is this minus this. So, this is the definition we followed for the Fourier transform. So, this is this and you have this is going to be minus 2 I times sine xi x dx, right. So, this sum is this difference, this minus this is minus 2 I times of that. So, what is this one? If you write like this, this is root 2 by pi integral 0 to infinity or rather 2 by pi goes comes out, because of this you have 1 by root 2 pi 2 by pi, that is x into e power minus x square t times sine xi x dx. So, this is the quantity for Laplace transform. So, sine transform Fourier sine transform is this. So, what you get is the same here. So, 2 goes. So, what you have is end up is minus I root 2 by pi times integral 0 to infinity x times e power minus x square t sine xi x dx. This is nothing but minus I times, this is actually Fourier sine transform of x e power minus x square t as a function of xi. Okay. So, you end up getting this one. So, this I is actually root 2 by pi times Fourier sine transform of this one. So, which is, so this implies I is root 2 by pi times I is this, and you have a root 2 by pi times Fourier sine transform. I replace Fourier sine transform from this, you have when you bring it this side, so you have I times Fourier transform of x into e power minus x square t as a function of xi. which is finally is I root 2 by pi times 1 by root 2 by 1 by root 2 pi. Fourier transform is minus infinity to infinity x into e power minus x square t e power minus I xi x dx. So, this is the quantity we need to evaluate. So, this I will be able to do by evaluating this integral. If I know this integral, then I know what is the I, that is Laplace inversion of e power minus a root s as a function of t. Okay. So, this quantity is, so let us look at Fourier transform of x into e power minus x square t, which is 1 by root 2 by pi times minus infinity to infinity x into e power minus x square t e power minus I xi x dx. This is straightforward. Directly we can evaluate by rewriting. So, to evaluate this, we evaluate this now. We evaluate this. So, to evaluate this, what we do is we cannot evaluate this directly. So, in a different way, to get this, to evaluate this, we first evaluate Fourier transform of e power minus, let us say x square times t as a function of xi. This is also a function of xi finally. Okay. This is 1 by root 2 pi times minus infinity to infinity e power minus x square t times e power minus I xi x dx. This quantity we first evaluate, and we make use of this to evaluate this, that we will finally put it here and get your Laplace inversion. That is the idea. So, let us look at this one first. So, how do I do this now? This I try to write, I put this in the form of e power minus x square type, okay, some e power minus something square. So, how do I put this like that? You have e power minus x root t, this is square, and you have plus xi x. Xi x, to get xi x, I have already have if I say a square plus b square. So, plus some b square 2b x root t, already x is there, x root t plus b square. So, that is what you have. So, what is this 2b root x? 2b x root t is actually is your my xi x. So, x x goes. So, what is my b is xi by 2 root t. So, you have xi by 2 root t. So, 2 goes here. So, this also will go. So, what is your b? B is xi b square, that is xi square by 4 t. So, this together is nothing but e power this. So, you have this quantity is already here, and of course, there is a I missing, right. So, you have let me write again. So, this is x square plus 2 x root t times b plus b square. So, what is my b? So, 2 x root t b is actually what I have is I xi x. So, this gives me x x goes, and you have what is b? B is I xi by 2 root t. So, if you replace there as b in the place of b, if you 2 root t you remove, you end up getting that, and b square, what happens to your b square? You have a minus xi square by 4 t, and this quantity is actually what you have here. So, this additional thing you have to multiply e power b square, that is minus b square. So, you have plus b square. So, this is going to be minus xi square by 4 t. Okay. So, let me write that. So, you have 1 by root 2 pi and you have minus infinity to infinity. I rewrote this part as e power minus x root t plus b. B is I xi by 2 root t whole square. So, if I whole square, if I want this integrand, I have to multiply e power minus xi square by 4 t. This is dx as it is. So, this is nothing to do with the integrand, with integral. So, you can write this outside. So, you have e power minus xi square by 4 t times 1 by root 2 pi, this integral minus infinity to infinity e power minus x root t plus I xi by 2. So, this is a constant square dx. So, I think we will not be able to finish today. So, let us wind up. So, before okay. So, this is let me rewrite this as e power minus xi square by 4 t 1 by root 2 pi, and this one minus infinity infinity. As we have seen earlier, if you consider this contour, this is your x axis contour, this is your y axis, okay. This is your x axis and you have 0 here minus r to r, and this is going to be xi by 2 root t. This is a constant, this is what you have, that is the point here. This point is, this value of this is I times this, okay. So, that is on the imaginary axis. You have this, you consider that much another rectangle like this, you will see that if you consider this integrand, you will see that integral over this contribution plus this contribution 0 as r goes to infinity. So, this is equal to this, if you want this one, this over this as r goes to infinity, you finally end up this one. So, that is same as saying this is equal to this one. So, you will see that this will be same as e power minus this over this is actually, or rather you should put it this way, over this actually this integral, and that should be same as this part, okay. This plus this is 0, that means this is same as this over this. So, that is e power minus simply x, this whole thing you can put it as some x root t plus I xi by 2 root t as some new variable, let us call this x 1, okay. So, you have dx is same as dx into root t equal to dx 1. So, even by contour integration, you have to justify by contour integration this by considering this contour, or in a formal way which is not legitimate, but formal way if you do also you get the same thing. So, if I get this one, dx I have to replace by dx 1 by root t, okay, that is as dx e power minus this whole thing as x 1. So, you have x 1 square. So, you have divided by root t times, so that I removed here, I write here. So, as dx 1. So, x 1 dummy variable, let us put it dx square, okay. So, this is same as this one. So, this is your Fourier transform of this one as this. This we already know that this is e power minus xi square by 4 t divided by root t times 1 by root 2 pi, this quantity is root pi, okay. So, let me write it carefully, this is root pi. So, the root pi goes. So, you finally end up getting 1 by root 2 t and you have e power minus xi square by 4 t. So, this is your Fourier transform of this. This implies Fourier transform of e power minus x square t as a function of xi is equal to 1 by root 2 t times e power minus xi square by 4 t. So, this is exactly what we have, and because of this Fourier transform, xi is positive, xi is between, xi belongs to 0 to infinity, Fourier transform, right. So, it is actually minus infinity infinity, okay. So, I can differentiate this with respect to xi. If you do, you will end up getting, or rather so okay, let us look at this part. let me look at this Fourier transform of this. Let me write what is this 1 by root 2 pi integral minus infinity to infinity e power minus x square t e power minus I xi x dx. This is equal to 1 by root 2 t e power minus xi square by 4 t. So, this is what we have. Now, t is also positive both sides. So, t belongs to 0 to infinity. I differentiate with respect to t if I do, or rather I think I should do with respect to xi. So, xi belongs to full R. So, if I differentiate with respect to xi, if I differentiate with respect to xi for example, what you get is, if you differentiate this with respect to xi, you get 1 by root 2 pi, a derivative you can take it inside, that is by Leibniz rule, this does not matter. So, e power minus x square t, and this you differentiate as it is, you get I xi x. If you differentiate minus I xi x comes out, I xi x, x will be here, xi will be here. So, this is dx as it is. This is equal to, if you differentiate this with respect to xi here, 1 by root 2 t times e power minus xi square by 4 t. Now, you differentiate this, you have a minus 2 xi by 4 t. Okay. So, 2 goes. So, you finally end up getting, this is your derivative. So, you have minus 1 by 2 root 2 times root t e power, that is going to be e power minus xi square by 4 t. So, from this you can see that Fourier transform of that is 1 by root 2 pi, you can get minus infinity infinity x e power minus x square t e power minus I xi x dx. There is a Fourier transform of this part is equal to, bring it to that side. So, root 2 goes. So, you have a root pi comes out this side, divided by 2 and divided by xi comes down, and you bring this divided by minus I, minus goes, you have minus I. Okay. So, bring it this side with this minus, you have minus I, root t is here, this part, and you have e power minus xi square by 4 t. So, this is exactly what you have. So, you get minus I by 2 xi times root pi by t times e power minus xi square by 4 t as your Fourier transform of x into e power minus x square t as a function of xi. Okay. Still always t is positive. So, what we do is we use this here in this, the Fourier transform of this is your Fourier transform. So, in the place of this if you put it, you will see, you will end up what exactly is your Laplace inversion. Okay. So, I will stop here, we will look at this, we will complete this in the next video along with other results, so that we can use application of, we will try to solve, we can use the Laplace transform to solve the boundary value, initial boundary value problems for the heat equation in other domains. Okay. We look into these boundary value problems in the next video. Thank you very much.